Yes. So you should have Windows to accept, and then you can reopen your camera on your mic. Did you succeed to do that? So Pietro, if you hear me, try to switch on your camera on your mic.
Yes, I succeed. Pietro, just click on the camera and you'll get. Then you can
switch on. Yes. So on the camera, try to reopen your camera, Pietro, on your mic. You have problem or give me in the chat. You can write in the chat if you have some problem.
One as well.
Okay, that's fine. That's fine.
Okay, fine. I found it.
You can try to share your slide.
Yes. I will. Where is it? To share. Where is the command to share?
Vertical arrow on the right on my
vertical. Another.
It's a partager share. It's a vertical camera, a vertical arrow in a box.
Vertical hand. Is that?
A vertical arrow.
A vertical arrow. I don't see it.
On the top.
Condividi vicino ad abbandona.
Oh, yes. Oh, yes, I found it. Okay. Just a moment. I am going to switch one. Okay. And now I should say
condividi.
Where is it? Condividi. Annulla. Okay, condividi. Condividi? No, that has nothing to do with it.
We see your screen.
Do you see my screen now?
Yes, but it's a text in Italian on a web page, I think so.
No, I mean.
So you have to select.
Yes. Now, do you
window.
see that? That is my transparency, my slides.
Chiudi tutti gli altri documenti, Pietro, chiudi tutto, tieni aperto solo quello che intendi proiettare. E poi ti clicchi quello e noi dobbiamo vedere quello.
Ok. Condividi.
Condividi.
Yes, on your select your slide.
Do you see the slides now or not?
No. You have to select you click on you have to open your slide before. And then select it. Yeah, open your slide. Yes, and now share, and you will select the windows where.
Okay. Select. Okay, I think I made it. Do you see it? Okay. I was not so familiar with with the teams. So, bonjour tout le monde. And I start by thanking in particular Frederic for this invitation that allows me to talk about a new development, not only Souriau thermodynamics, but I'm going to talk about the context in which these new developments are inserted. I will start by saying that essentially, I think, although we never met before, but from his activity, I can understand that Frederic shares with me the idea that the world of machine learning can make significant progresses on top of what is already achieved by inserting a good large portion of geometry into the texture of its of this discipline. Okay, so now if you see my first transparency is just a figurative summary of my talk. I try to symbolize a little bit the whole idea. You see King Arthur in the capacity of geometric deep learning. And on both sides of King Arthur are two paladins, Cartan and Adamar. That symbolizes the fact that I will use results and theorems by both of these important mathematicians to justify what I'm going to talk. In particular, my talk focuses on the following setup. On one side, we have non-compact symmetric spaces, U over H. And on the other side, we have solvable Lie groups, where S is a subgroup of U. The fact is that in the supergravity community and in the long development of supergravity over the last 50 years, it became at a certain point evident what we call the metric equivalence, which is a particular declination of general theorems by Cartan and Adamar. Namely, the non-compact symmetric spaces are as manifolds equivalent, just identifiable with solvable Lie groups. And that provides something that in the world of supergravity had particular relevance, namely the fact that there are special parameterizations of the U over H manifolds by means of coordinates that are just parameters for the solvable Lie group. Now, in order to do thermodynamics on the symplectic, on the U over H, we need the symplectic structure in order to define moment maps. So that will, at the end, select among the U over H the Kähler ones, as I will. So all are the ingredients, the various swords of the round table that point towards Souriau thermodynamics. Now, my starting point is the sort of obvious things to say that geometric deep learning from the mathematical point of view has two pillars on which it is based. On one side, differential geometry, and differential geometry occurs as a modelization of the layers of the network. And on the other side, probability theory, because all the algorithms of a neural network of machine learning are probabilistic kind of algorithms. So probability theory and differential geometry. In my talk, I will try to see how they are intertwined, and there is cooperation between the two sides and the two pillars. So I will start with pillar number 1, differential geometry. The focus of my talk is on the second pillar, but I cannot tell you what I have to say on the second pillar without summarizing the new vision and format that we have developed over the last 2.5 years about the first pillar, namely the differential geometry that pertains from our point of view to neural networks and machine learning. So I'm going to summarize as fast as I can, because I want to turn to the second pillar, but I cannot skip that. The global geometric approach to machine learning, based not on modelization and choices, optional choices, but from our point of view, from first principle. Let us begin with a preamble on the global geometrization of machine learning that eventually we have named Cartan neural networks, just because of the role that Cartan thinking has on all that we have been doing. So this is a long-term project that started in 2023, and I just summarize how it was born. I had never been involved in machine learning and neural networks, but I was stimulated by my friend Souriau, who is not a physicist, rather is an economist, to think about machine learning and PhysMath. In the spring of 2023, I tried first to learn what neural networks are, and next to think which conceptual contribution I might provide to this field. Unexpectedly, I discovered two things. On one side, that was the very first impression I got. The standard conception of neural networks, notwithstanding their great successes, is plagued by an original sin, a mathematical discrepancy that is quite serious, yet it is essential for the functioning of the algorithms. So that my first thought was, how could I remove this original sin? And I discovered that this sin can be the removal of the sin can be obtained by importing into machine learning a large fraction of the mathematical lore developed in the context of supergravity on the basis of advanced classical differential geometry. This is how this project was born. It took about 2 years to develop my thought and together with my co-authors, but the year 2025 was the year where we started producing, and in 1 year we produced 6 papers, rather ponderous, that I just mentioned for your knowledge, but I'm going to discuss them, because otherwise I use all my time discussing the content of the other 5 papers. The present talk is mainly concerned with the 6th paper that has a title very similar, almost identical with the title of this seminar. So the beginning is a critique of present-day neural networks. At the end of the day, neural networks are just many parameter ansatz for an unknown function. And there is an historical, of course, reason for what I describe as a sin. It is the fact that the neural networks evolved as multi-layer arrays of perceptrons in the way that it was defined by the founder of this field already in the war years, and then coming down to Rosenblatt in the 50s. And from this vision, that was that of trying to imitate the behavior of physiological neurons, came the original scene. But what actually nowadays neural networks are just something quite different from the original thought. They are just, as I said, a setup to construct a many parameter ansatz for an unknown function. And the thing is that this way of constructing the ansatz is based on a series of maps from the input that I call x0 and the output that I call y, that are conceived as vectors, going through intermediate vectors of various dimensions. And the map from one vector to the next one is something that is just an affine transformation, where W is typically a rectangular matrix because the dimension of the various layers are different. So a linear transformation is described by a matrix, which is rectangular, followed by a translation. So that is why it is affine. And the names given in the community of machine learning for these two things are W, because this is the matrix of the weights, and B is the vector of the biases. And up to here, everything is okay, but it is necessary to introduce nonlinearity. And nonlinearity is introduced by means of the so-called activation functions that are nonlinear transformations of individual components of the vectors. This is the discrepancy. The discrepancy in the sense that one pretends that these guys should be vector spaces, and the linear transformation is the core of the whole learning, but then needs nonlinearity and destroys the very nature of vector spaces, because after the application of the activation functions, no change of basis is any longer permitted. So I tried to understand how this can be cured. Mathematically, the construction of the ansatz should be mathematically well-defined, self-consistent, and interpretable within a geometric or an algebraic theory. This interpretability is very important. Mathematically, the definition of the nonlinear map we have shown is anomalous, independently from the choice of phi, since it's not covariant, as we said. In the Cartan neural networks that we proposed, and we also constructed in some instances with some choices, the maps from one layer to the next are homomorphism and isometries, so that the conceptual problem I am signalizing is resolved, is overcome from the very start. Let's go briefly through this argument. The vector spaces should be rather interpreted as coordinate patches for a differentiable manifold Mn. And therefore, the layers should be interpreted as differentiable Riemannian manifolds Mn of dimension n. And now the maps between two differentiable manifolds should be a smooth maps between manifolds. Nevertheless, we should capture the main idea that these maps are codified through linear transformations, because otherwise we lose the whole idea of weights to be learned in the procedure. So the only generic way of obtaining nonlinear smooth maps between manifolds, starting from a linear map between vector spaces, is when the considered manifolds are Lie groups. And we work out the map from one group to the next one from a linear map of the corresponding Lie algebras. In view of the above, the nonlinear map that substitutes the activation function has to be the conceptually unique exponential map from one Lie algebra to its own Lie group. Now, in this context, it seemed at first sight rather strange that the network layer should be Lie group manifold. Yet general theorems come in our aid if we think about what are the basic needs of neural networks algorithms. All NNS algorithms view data as points in a space and analyze their relation on the basis of their relative distances. Points that are near to each other are correlated, while those that are far away from each other have weak correlations. That is a general thing that is applied at the basis of all algorithms. That is not something without a price and a suggestion. Namely, we said that the layer should be manifolds, Riemannian manifolds. But Riemannian manifolds typically do not admit a unique notion of distance between points. Now we will see what the theorem tells us. On the other hand, only distances, relative distances should matter. Namely, all points of each MN should be equivalent. And that in mathematical parlance has a name. The manifold should be homogeneous spaces. So the Cartan neural networks follow from first principles. If we, and as everything in mathematics, there must be a beginning point. The beginning point is that if we accept the two requirements of existence of a distance function and of homogeneity, then we are almost there because of theorems. In order to have a square distance function between any 2 points of the Riemann space Mg, it is necessary that the geometry of the latter provides a unique geodesic arc connecting any pair of points P1, P2. Then the distance will be the length of such an arc. The only simply connected manifolds with the above property are the Cartan-Hadamard manifolds, namely those non-compact, simply connected Riemannian manifolds whose sectional curve is non-positive at every point. This is the definition of Cartan-Hadamard. And then Cartan-Hadamard provided us also with a very important theorem. Every Cartan-Hadamard manifold of dimension d is diffeomorphic to R of d, power d. Namely, as a differentiable manifold, we can cover the full manifold with a single chart, open chart, and this single open chart is what provides a universal set of coordinates. Now, if we need also homogeneity, then the only generic option is that the Cartan-Hadamard manifold should be what is known in the literature as an Alexeyevsky normal Riemannian space. What are Alexeyevskian spaces? An Alexeyevskian normal Riemannian manifold is a Cartan-Hadamard manifold M that admits a solvable Lie group of isometries with free action on transitive action on M. Free transitive action means that as a differentiable manifold, the Alexeyevskian normal Riemannian manifold is just a solvable Lie group. It coincides with its group of isometries. And Therefore, Alexeyevskian manifolds are defined by a pair where S is a solvable Lie group and G is the metric induced on this solvable Lie group by a norm defined on the corresponding solvable Lie algebra. This norm should be, this scalar product, if you like, should be positive definite and non-degenerate. So it is certainly not the Cartan-Killing metric, and invariant with respect to the solvable Lie algebra. This is a chapter of mathematics where there are a lot of papers and work about the normed solvable Lie algebras. But the important thing, which is a Sugra heritage, an heritage of supergravity, is that non-compact symmetric spaces U over H with a solvable Lie group are equivalent with the solvable Lie group. And that was essentially pointed out and developed by Trigante and myself in the middle 90s. In fact, it was essentially the main topic of Mario Trigante's PhD work at CISA under my supervision. And then it was extensively developed by the same authors with Adrianopoli, Dauria, and Ferrara, and also other authors in the following years. The solvable coordinates on U over H are the solvable Lie group parameters. And this solvable Lie group parameters provide the explicit realization of the diffeomorphism claimed by Hadamard and Cartan of U over H with an RD manifold, because the solvable coordinates are just free coordinates, free with no constraint. They just go from each of them from minus infinity to infinity. Now, this is a great result. Homogeneity and existence of the distance function, we have selected those manifolds that are symmetric U over H spaces and are metric equivalent to as many solvable Lie groups. Since they are Cartan-Hadamard manifolds, they are, as I said, diffeomorphic to Rn, and the use of the solvable coordinates is an extremely important weapon. It remains to say what is the characterization of the maps between hidden layers. Here I will be very sketchy because I have no time to go into these details in order to arrive at the next topic of interest to us, the focus of the seminar. But I will just tell you in a few words the idea. Because of the metric equivalence, if the point in the symmetric space is represented with a symmetric matrix, depending on its the coordinates, the solvable coordinates, which is possible for all of these symmetric spaces, then there is some operation that gives the corresponding solvable Lie group element. A logarithmic map that we call sigma minus 1 gives the corresponding Lie algebra element. Then we can make a linear map into another solvable Lie algebra, which is a homomorphism of Lie algebras. And then we go the opposite way. We make the exponential map to the solvable group, and then we make the inverse of this operation here, which gives a point in the symmetric space. After that, we can still act on the result with the full group U over I, Ui plus 1. And that is an isometry. And this isometry the parameters of this isometry are the analogs of the bias in the normal formulation of neural networks, while the matrix describing the homomorphism is the analog of the weights. Okay. Instead of going on, neural network theorems, great result, schematic, covariance and interpretation. This factor.
You have stopped to share your slide, so you have.
Okay. Sorry.
You have to share again.
I have to share again. Okay, I will try condividi. Finestra. Okay. Condividi. Do you see it now?
Yes, that's fine.
Okay. So such construction immediately implies that there is a covariance in the sense that I can act on this compound that is the map on the left with transformations of the group ui plus 1, and on the right with transformation of the other group. And this will provide a redefinition of the biases and of the homomorphism matrix. So this is what we think is the main prize for using this point of view on networks. The ingredients now become interpretable, and because of this covariance. Now, this is what I wanted to say on the first pillar. Now I go to the second pillar. The second pillar is probability theory, and here I will argue in the following way. I will go through 3 steps. In the first step, I will try to outline, I aim at showing more than the formula and the results of the logic behind what I'm saying. So the logic is that there is a generic way of defining thermodynamics, the geometry of thermodynamics, by means of the following ingredients. I have a manifold of events, as it is usually called in probability theory. That space of events might be something more complicated than a differentiable manifold, but let us think that is just a differentiable manifold to begin with, for simplicity. We have some collection of functions defined over this manifold, and then we can start doing thermodynamics. These are the 2 inputs: functions, collection of function on a differentiable manifold. With these 2 ingredients, whatever they are, we arrive at a structure of contact manifold in the thermodynamical space, which is always odd dimensional and has a almost foliation. It's not a real foliation, precisely because it is a contact manifold, but it's something similar to a foliation, where I will try to explain to you what these leaves are. They are submanifold of 1 dimension less, codimension 1, that are in state symplectic. That is the first point. The second point is that now we ask ourselves, what are the appropriate choices within what we would like to do of the function xi of q? And the answer is that they are to be identified with moment maps of vector fields. In order to have moment maps, this requires that the manifold of events should not only be a manifold, but should be a symplectic manifold endowed with a symplectic structure. The symplectic structure is what provides the possibility of having moment maps. Now, recently, very recently, we understood that this function might be just the moment maps, but can also be polynomials in these moment maps. This is something I only quote for completeness, but because it's work in progress. The third point is that once we have decided this, there is a bifurcation. The bifurcation is that the manifold of events is symplectic, but there are two ways of thinking of a symplectic manifold. Either as the generalized phase space of a dynamical system, in which case the moment maps are really Hamiltonians in the sense that there is a principal Hamiltonian describing for a dynamical system its evolution, and the other are additional Hamiltonians that can be defined in this framework. And this allows, as we can see, a certain kind of interpretation. But another interpretation that is the one relevant for us and for supergravity applications and also for algebraic geometry is that the manifold we are talking about is not only a symplectic manifold, but it's also a metric manifold, and the combination of the two things means that it is a Kähler manifold with a maximal group of isometries in particular. And then the relevant moment maps are those of the Killing vector fields that, because of the Kählerian structure, are all Hamiltonians. Souriau thermodynamics is placed in this conceptual framework. So let us see what is the generic approach to thermodynamics. The generic approach is due to Shannon and as I'm going to emphasize, to Jaynes. It's an old story that dates back to 1957. Shannon introduces famous functional, and the relation with thermodynamics is that his famous information entropy can be thought as the real entropy of thermodynamics. But that becomes well understood once one goes all the way down to geometrization of thermodynamics. And this will be the contact manifold structure I already anticipated. And in this case, what will happen is that thermodynamical equilibrium states are geometrically identified with Lagrangian submanifolds within symplectic geometry. So this is the full symmetrization of thermodynamics. Let's see how it goes. It goes in a rather simple way at the beginning. The connection between thermodynamics and probability theory is that in probability theory, we are interested in probability measures, but now I have simplified the thing by saying that my manifold of events is only a differentiable manifold. And then we can speak in terms of probability density. So there is some probability density, and the Shannon entropy is given by this integral, the probability times its log integrated over the manifold. On the other hand, if I have any function on the same manifold, the average value of this function is clearly given by this other integral. What Jaynes did in 1957 was to rederive from the extremization of Shannon entropy at fixed mean value, the whole compound of classical statistical mechanics and thermodynamics. It goes in a very simple, almost exercise way. You have the norm of the probability density that should be 1, because otherwise it's not a normalized probability distribution. And now you use variational calculus, the usual approach with Lagrangian multiplier. You have two constraints to impose in the extremization of the function, of the information function. One is lambda 0, the first Lagrangian multiplier that imposes the constraint that the norm is 1. And the second is a vector of Lagrangian multipliers that imposes the constraint that the average value of whatever are these functions that we have is equal to some number x that we want. Now, the answer of variational calculus is very simple. The normalized distribution is given by this expression, which is the form of so-called Gibbs probability densities. For each function, we have all the collection of functions, and the denominator is the partition function, namely the integral of the numerator over all the space. Now, this being the thing, thermodynamics, we have to recall things that are customary and to us well known even from high school almost. In standard physical thermodynamics, there are two kinds of variables: intensive and extensive variables. Typical intensive variable is the temperature. Others are the chemical potential, for instance. While the typical extensive variables are, for instance, internal energy or volume. Now, you can make the thing more complicated, but this example is sufficient to understand the difference. Now, in this geometrical interpretation, the intensive variables are to be identified with the Lagrangian multipliers, lambda 1 up to lambda n, while the extensive quantities have to be identified with the average values of the xq functions that we have introduced. So doing, we arrive at contact geometry. Now, I cannot give an entire course in a few minutes on contact geometry, which is an entire chapter of differential geometry, dating back to the 19th century, by the way. But I try to summarize the main point that in the definition of what a contact structure and a contact manifold is, that allows to make the connection with thermodynamics. A contact manifold is a odd-dimensional manifold, and the contact structure over this odd-dimensional manifold is a rank 2n subbundle of the tangent bundle that can be identified with the hyperplane bundle associated with a one form, alpha, that is required to satisfy this constraint. Alpha wedge the differential of alpha, which is the two forms, n times, wedge, n times, should be different from 0. It is like saying that this one form is of maximal rank. When alpha satisfies this constraint, then alpha is a contact form, and the contact structure is that subbundle of tangent vectors, vector fields, such that they are in the kernel of alpha, namely all vector fields on which alpha makes 0 are members of the contact structure. Now, the very important thing that dates back to the 19th century, to Darboux, is that on any contact manifold and in every patch, in every coordinate chart of this contact manifold, we can choose coordinates of Darboux type, namely a set of coordinates in which the contact structure has this special form. The coordinates are 2n plus 1, so we have pairs of coordinates y and xi from 1 to n, and then there is an exceptional coordinate x0, and the contact form has this particular Darboux form. So it's important that we can always find the local patch in which the contact structure has Darboux form. Now, the connection with thermodynamics becomes evident from Darboux coordinates. All of thermodynamics is encoding in stating the expression of the contact one form. Alpha is just the differential of the entropy, the Shannon entropy, plus lambda I times dxi. Let's compare this with the classical thermodynamics of high school. For the simplest possible physical system, we have 5 thermodynamical variables: the entropy, the internal energy, the volume, and the pressure. Now, the Lagrangian multiplier we can identify with the first with 1 over the inverse temperature, the second with the pressure over the temperature. And the entropy is a part. Now, clearly, if we use this identification in the contact form, we find that the contact form is minus ds, because typically we identify the physical entropy with minus the information entropy. Then T minus 1 du plus T minus 1 P dV. And now you see that saying that the alpha vanishes is equivalent to stating the first and the second principle of thermodynamics, because this is multiplying by T. The statement that something is 0 is true if we multiply it by T. We get du plus pdv is equal to something, and that something must be equal to ds times t. Therefore, of course, this is the heat, and these are the first and second principles of thermodynamics. But the point is, what does it mean that alpha vanishes? Obviously, it should not vanish everywhere. Otherwise, why should we have introduced it? The fact is that it vanishes on special submanifolds of the contact manifold. And where it vanishes, those are the equilibrium states of thermodynamics. So now we have a geometric characterization of the equilibrium states. We can say that the equilibrium states are Legendrian submanifolds. To explain this nomenclature, we first have to say what is an isotropic submanifold. An isotropic submanifold of a contact manifold is a manifold whose tangent submanifold whose tangent bundle is in the kernel of the contact structure. Now, if an isotropic submanifold has the maximal dimension, then it is named a Legendrian submanifold. So, Legendrian submanifolds are those where the first and second principle of thermodynamics hold, because the contact form vanishes on them. This is the full geometrization of thermodynamics. Now, from contact geometry to symplectic geometry, and we will see how the so-called information geometry arises. We just need one more notion that of contact geometry, that is the notion of Riepp vector field. A Riepp vector field is a vector field over the contact manifold, which has the following property. Evaluated on the Riepp field, alpha makes 1. Furthermore, evaluated on the Riepp field and on any other vector field, the differential of alpha makes 0. So this means that the Riepp field is the opposite, is exactly the opposite of the contact structure. It is the field that is transverse to the contact structure, which is in the kernel. Now, when we have this vector field in Darboux coordinates, it is obvious what it is. The Riepp field is just the field that is just the gradient in the entropy variable. If we look at those manifolds that are transverse to the Riepp field, submanifolds that are transverse to the Riepp field, so I have only coordinates lambda and x, the Riepp field is frozen to a constant, the entropy is frozen to a constant, then you see that d alpha restricted to this manifolds is just as a maximal rank 2 form, which is by construction closed. So that provides a symplectic structure on all the submanifolds that are transverse to the Riepp field. And of course, there is a projection from the contact manifold to the symplectic manifold, which is in Darboux coordinates means simply to ignore the entropy. Now, xi, the coordinate, the thermodynamical coordinates xi were defined as the average values of the functions we were interested in. And by definition of the partition function, if we take what is called the stochastic Hamiltonian, in it's the analog of free energy in classical thermodynamics, namely minus log of the partition function. If we take the derivative with respect to lambda, by definition, this provides us with the average value of the function x. So the equations that embed equilibrium states are stating that xi, the variable xi, is equal to what we want, the average, its average value, the average value of the function by this. So this is the embedding equations. And if we take the projection on the symplectic subspace, the Legendrian submanifolds that are defined by this, the Legendrian submanifold becomes Lagrangian submanifold, namely submanifolds on which the symplectic form is equal to 0. Well, it's equal to 0 because the Hessian of the symmetric, by definition, the Hessian of the stochastic Hamiltonian, and therefore, with the anti-symmetrization due to the wedge products, it becomes 0. In information theory, the Hessian of something is what people describe as the information, the metric of information geometry. Now it comes from thermodynamics.
Fisher information. Fisher.
Sorry?
Fisher information.
Yes, yes. Okay. This Hessian derives in a logic way from the following argument. We should think what is the metric on the contact manifold. The contact manifold we define so far only by the presence of the contact one form, but it has also a metric. And the metric in their book coordinates for the contact manifold is this one, the entropy square, and then this metric with the Hessian here and the inverse of the Hessian here. Why is it that so? Well, I tell you why. It comes from the fact that in their book coordinates, the Lagrangian submanifolds have obviously the metric that is obtained by just deleting the entropy contribution, namely this. And why is this the correct metric for the Lagrangian submanifolds? The answer is simple, because we know that this metric here is just a Kählerian metric, because it is a metric that is a Mission with respect to a complex structure. And the complex structure is obvious. It is just this object here. And this object here, multiplied by the metric, that is this matrix here, makes what we already know, namely the symplectic form. The symplectic form we already knew, and therefore the metric that is consistent, the most general metric that is consistent with the symplectic form to be the Kähler form is the one in this yellow font. Now, what is impressive is that this form of the thermodynamical metric on Lagrangian submanifolds is identical with the form of the Kähler metric in toric varieties, in the so-called MC symplectic formalism, Abreu, Martelli, Sparks, and Yau. And it is the form of the metric of the Kähler metric that applies when the Kähler potential depends only from the moduli of the complex coordinates in some complex chart. Then G is the so-called symplectic real potential, which is just the Legendre transform of the Kähler potential. And theta I are the phases of the complex coordinates. Now,
so
you can learn more.
It is also related to action angle
Yes,
coordinate. Yeah.
Yes, it is exactly action angle coordinates. But the fact, the important thing is the relation with the Kähler structure. That occurs only when the Kähler structure, the Kähler manifold has a toric symmetry, which means that the Kähler potential depends only on the moduli of the complex coordinates. More about that you can find in my lecture notes of 3 years ago, if you want to.
Also, just in information geometry, it corresponds to the dual system of coordinates.
Yes.
That correspond to the dual potential function, the entropy on the what is called the Massieu characteristic function, which are exactly the analogy information geometry.
Yes, you see now that if you substitute in the previous, now this is the analog. If you substitute the value of the axis, the embedding functions for the axis and the Lagrangian, here you obtain h twice with h minus 1 that make just 1h. And so this becomes, this term becomes identical to the previous one, and therefore the pullback of the full metric onto the Lagrangian submanifold is just the metric apart from a factor 2 in front, which is disregardable. It's just the metric that is usually understood as information metric. I think this is an action angle is certainly exactly the same, but the point is that this structure is absolutely general from this point of view. So summarizing, we can say that we have a general scheme to go from probability theory to thermodynamics. In this scheme, we find contact geometry, and we have a characterization of the equilibrium states as Lagrangian submanifolds, first Legendrian, then Lagrangian. And on the Lagrangian manifolds, we have a Kählerian metric, which is related to the metric used in here. Laplacian is just should be Lagrangian. I wrote Laplacian instead of Lagrangian. Okay, but this is completely general. So the next question is, what are the XQ functions that of our interest? And here you see Sir William Hamilton that is switching on the fire, because in order to come close to our use of thermodynamics, we would like that the XQ functions on omega space of events should be moment maps of Hamiltonian vector fields. And this can happen if and only if the omega is a symplectic manifold. So an Hamiltonian representation of the vector fields. Just a flash, because there will be an entire seminar after me about coadjoint orbits. I would only remark that coadjoint orbits are always diffeomorphic to coset manifolds, because as a differentiable manifold, they are the quotient of the group with respect to the stabilizer of the element of the Lie algebra we are talking about. And this stabilizer is never empty, is never the identity, because at least it contains lambda itself. So considering coadjoint orbits is equivalent to consider all possible coset manifolds. We are focusing on particularly a type of coset manifolds, the U over H, and in this category for thermodynamics, we are interested in those that are Kählerian, namely in those that are also appropriate coadjoint orbits. But this is meant to say that if you talk in terms of G over H, you do not miss any coadjoint orbit, because coadjoint orbits are always cosets. Now we have a bifurcation. The bifurcation is the following. due to Sir William Hamilton, we have a manifold that is symplectic, and we have Hamiltonian vector fields. But now the question is the interpretation. The interpretation can be, on one side, that indeed we are dealing with a dynamical system. So these Hamiltonians are really Hamiltonians in the sense of dynamics. And among them, there must be one special one that is the one associated with the time flow, and so on and so forth. But the other possible way of looking at the whole thing is that instead we consider the symplectic manifold to be a Kähler manifold, or even an hyperkähler manifold that is in particular Kähler. That means that there is a complex structure, and the complex structure together with the symplectic form produces symmetric, or vice versa. And the Hamiltonians, namely the moment maps we are interested in, are not all possible Hamiltonians, but only those associated with Killing vectors of the metric. There is, from this point of view, there is no time flow, no principal Hamiltonian, and integrability is not an issue in this kind of interpretation. So the interpretation and use of moment maps that occurs in supergravity and brain physics is this second one, typically. And I would like to stress that it is the second interpretation that is also the one relevant for Souriau thermodynamics, but also for another, just to show that the thing is broader, to another province of mathematics, differential geometry and algebraic geometry together, when you try to find crepant, so-called crepant resolutions of quotient singularities via Kähler and hyperkähler quotient. That is what Kronheimer has first done for hyperkähler, and has been later extended also to Kähler only. I have worked extensively on that issue, and was of particular relevance also this in supergravity and string theory. For my contribution to this, I quote again my lectures in Berlin, in Potsdam of 3 years ago. But this is just only to say that this way of looking at the moment maps is quite rooted in different directions. Now, finally, Souriau thermodynamics. I'm finally coming to it. But I've piled up all the items that are necessary, the conceptual items. So why Souriau thermodynamics? Just because we already decided what are the manifolds that provide a good modelizations of the layers of neural networks. They are U over H symmetric spaces. And on the other hand, if we want to do statistical distributions on these layers, we need to do some thermodynamics. This thermodynamics becomes well defined if, in particular, these layers are Kähler manifolds. And then we have all the structures I have been discussing, and Souriau thermodynamics becomes absolutely canonical. Namely, we consider Gibbs distribution given in this way, where the Gothic P means the moment maps of the Killing vectors namely which are in the Lie algebra of the group U, as much as the temperature beta. And the partition function is just the integral of this numerator with the appropriate measure on the Kähler manifold, which is the n times the product of the Kähler two form. The essential point is that the integral should be convergent. And that is the really intriguing definition of Souriau thermodynamics. What are the betas that make the integral to be convergent? So Souriau introduced the notion of temperature space, that is the set of betas for which the integral converges, which is a subspace of the Lie algebra. Now, we have an answer for the omega t. The answer is the following. This integral becomes convergent if omega beta is in the adjoint orbit with respect to the full group of a convex cone in the Cartan subalgebra C of the maximal compact subgroup. Now, here I have to say a caveat. This is true for lower dimensional symmetric manifolds of the type I have described. Our recent discovery, which I'm not going to talk about because it's work in progress, is that in the case of larger manifold beyond a certain limit, one has to extend the Cartan subalgebra of the compact subgroup with a billion extensions, including polynomials in the moment maps of the compact subgroup. I am saying only that as a caveat. Now, let me just outline the proof of what I said in the format that applies for lower dimensional. The results that I mentioned comes from the following four ingredients. A, the use of solvable coordinates, namely of the Kählerian, the equivalence of the Kählerian manifold with the solvable group. B, with the formula, generalized form, general formula that was derived 30 years ago by Trigante and me for the moment maps in such a situation. C, from the cyclic property of the trace, and D, from the U invariance of the integration measure. Now, I just mentioned extremely briefly the formula, which is extremely simple. The formula for the moment maps includes the generators of the Lie algebra, the coset representative, which is a solvable group element, but also U element, of course, in depending on the solvable coordinates, and the object xc, which is just the generator of the U1 factor in H. The U1 factor is that responsible for having a Kähler structure. This is a very simple formula, but from this very simple formula, with a few almost obvious arguments, we derive the fact that beta of the moment map evaluated in the image through a generic element of G of a point in the coset is just the same object in the point, in the original point W, but with a beta that is the adjoint transformation of the previous beta with respect to the G. Since the measure is insensitive to G, that means that the function, the partition function, is invariant. So, since the partition function is invariant, two things follow. First, that the partition function actually does not depend on the individual betas, but depends only on invariants constructed with beta, Casimirs of the Lie algebra. Secondly, it means that we can always rotate beta to a canonical beta that is placed in the Cartan subalgebra of the maximal compact subalgebra. And the convergence of the integral can be studied in terms of the beta zero, which for low dimension is rather easy. And it was done in explicitly in two cases, for SU11 and for SP4. And also it appears that we can easily do it for up to a certain value of the extension in what I will describe as Calabi-Visentini manifolds.
Just one remark, because in the model of Souriau, you have also the case of non-null cohomology when you have an additional cocycle, so it addresses the larger problem also in case of cocycle, when you have the coadjoint operator is not equivariant, but you have a cocycle.
Yes.
It's addressed in Souriau, but it doesn't matter. So the logarithm of the partition function is not invariant, but the Hessian is invariant. It's why the Fisher metric, also in the case of cocycle, is invariant under the action of the group. But Souriau also address the case of non-null cohomology on when you have a cocycle.
Okay, the cocycle is probably related with this extension we are talking about.
Yes, so sometimes people, so you can use a central extension to make disappear the cocycle. But for Souriau, it is important. For instance, for Galileo group, the default of cohomology on the cocycle is related to the mass in classical mechanics. So this cocycle in physics is meaningful. So it's very important to manipulate the cocycle, because it makes sense. And so for the Galileo group, or for affine group or subgroup of affine group, you have this cocycle. For SO3, you have this cocycle, and so it's important to manipulate, and it will be interesting, yes, to make the link with your previous concept. And
yes, certainly. What I note from your observation is that the groups you mentioned with that have cocycles are not simple or semi-simple.
Yes, so for your case of non-compact group, you will not have a cocycle on that. Yes. So for your case, you have not this cocycle, I think so.
Yes,
for example,
that is
for SU11, you have it is the coadjoint operator is equivariant, and you have no cocycle. For SU11 or SUNN for Ziegel space.
Yes. We are dealing only with the simple Lie algebras in this approach. But there is another problem that involves that can be cured with what I mentioned briefly, but it is really very, very, very recent discovery, so I cannot comment, but I wanted to just to tell you that we know how to solve that problem, but we have to study more for all the details, essentially.
Yes. On another remark also, the case of convex cone. So this is a link with the work of Jean-Louis Causul, who has also introduced a metric for sharp convex cone, which is related to what is called Causul-Weinberg characteristic function.
Yes.
The man, Jean-Louis Causul, was a PhD student of Henri Cartan, but he works on one topic given by Élie Cartan, is the study of homogeneous bounded domain.
You said Henri or Élie Cartan?
He was a PhD student of Henri Cartan, but the topic of his PhD was a question given by Élie Cartan.
Oh, okay.
The study of homogeneous bounded domain. So you can take the Poincaré disk as an example, or the Ziegler-Upper plane, as you want. So you have a sharp convex cone, and you look for a metric which is invariant by all the automorphisms of this sharp convex cone.
Yes.
And you find exactly the same relation that for Souriau or your relation, and you will find that the good metric will be the Fisher metric. So it will be the Hessian of the, what you call partition function is called the Causul-Weinberg characteristic function, and then you take the Hessian of the logarithm to introduce an invariant metric to all automorphism of the sharp convex cone. So it's a relation. Yes. So I will send you some publication of Causul on this topic.
We have to look at this connection with Causul. Yes, certainly. But certainly maybe I mean, if you want to know more, in the audience there is my co-author Alexander Sorin, who has discovered this extra nuance, and he can comment if he wants on that point. Sasha, do you want to comment on this that was said?
Thank you, Pietro. I think that quite soon we submit paper in full details, because it requires some time slot, and I see that your seminar is almost over, because in 1 minute it will be just 2:30.
Yes.
So I give you floor and privilege to talk.
Okay. But I'm almost there. I mean, I have a couple of more transparencies. This is the standard. I will not say much more about that, because now it is clear what it is standard. You just go to the beta 0 and you consider all possible shifts of the point. And I can flash through the result that we obtained for SU11 that coincides with the result by Charmar and Barbaresco, and probably the only different notations. And I can also show some of this Gibbs distributions over the plane, the disk. And finally, I can say that this is the main point. I still wanted to give a couple of remarks. The Kählerian U over H with U simple are just only two towers of manifolds. The Calabi-Visentini manifolds, that are these ones, and the Siegel planes. Now, in here, this is what I really wanted to stress. From the point of view of doing Souriau thermodynamics in this way, they are both equivalent, but then for application, there is a difference. Namely, Siegel plane grows in non-compact rank, which can be a difficulty, and moreover has no Tizatake projection. I had no time to talk about the Tizatake projection, but I would like you to know that in our development, we give a lot of emphasis to the Tizatake universality classes that were already, it is a concept that was already introduced by us in the context of supergravity. And the Calabi-Visentini are just one Tizatake one Tizatake universality class. Furthermore, in the Calabi-Visentini case, there is the notion of paint group, which is not so much well known in mathematical community, but was pointed out in supergravity by myself and my collaborators at the time, and then with Mario Trigante and with Tuan Van Prooyen, we made the systematics of the paint group symmetry. Now, I have the thought that the paint group symmetry can be quite relevant for grouping data into similarity classes. So the preference to study, first of all, Calabi-Visentini is because of this remarks, and for the final one, that in categorical perception, as named by in some context, or classification task, which is the same thing named in other context, what is particularly relevant is the existence of separators in the layers. Separators are codimension one manifold with certain properties that allow you to separate what is on the left and what is in the on the right of this codimension one manifold, and it is an ingredient in constructing categorical perception tasks. So for all these, and for the fifth reason is that Calabi-Visentini anyhow are embedded in Siegel. So studying Calabi-Visentini means to study also Siegel planes, but with some constraint. So for this reason, I think from our point of view, the most challenging new developments will be by studying the networks on Calabi-Visentini manifolds and at the same time their Souriau thermodynamics. And with that, I thank you for your attention, and I stress that this last remark was not only the statement of some programmatic points for our work, but maybe also how to say, suggestion for possible collaborations. Thank you very much once again.
Thank you very much. We have a few time for question, one or two questions in the audience. Do you have question?
Well, that depends on our leader. I'm happy to answer any question, but.
No, I have no question, but it's very interesting because especially the link with the work of Abreu on the link with action angle coordinates, because what is interesting, we are exploring in our seminar is dissipation. And dissipation is linked to the transverse structures to this symplectic foliation generated by coadjoint orbit via the moment map, Souriau group. So it would be interesting to see with your model also. On my question, more general question is the seminar. It's what does it mean dissipation in machine learning? Okay. For my understanding, for the time being, machine learning is using only non-dissipative process on what is dissipation in machine learning. And to study dissipation, we have to explore the dynamic which are transverse to this symplectic foliation, transverse to the level set of entropy and generating entropy, in fact, because you are moving from one leaf to another of the level set of entropy. So for the time being, we have invited people working on metriplectic flow because you have a link between Poisson bracket to describe non-dissipative dynamics on a metric flow bracket describing a dynamic which is transverse to this foliation. On the interpretation in thermodynamics that you have, in fact, you have two foliation. You have one foliation which is foliation which are the level set of entropy, and it's why that in the model of Souriau, entropy is a Casimir function. It's a Casimir function on the symplectic manifold generated by the coadjoint orbit. But transversely, you have Riemannian foliation, which are given by the level set of energy. Okay.
Level set of what? Sorry, I missed
energy. Of energy.
Of the energy. Yes.
Okay, for classical thermodynamics, but you could extend because the moment map capture all the invariants. So the energy could be invariant, but also the angular momentum. So in the model of Souriau, it will be the heat that is the mean value of the moment map that capture all the invariants. But this idea is that you have this kind of web tissue in French between your two transverse foliation. And for the time being, we explore, because it has been studied, this structure has been studied by Paulette Lieberman in his PhD study. So Paulette Lieberman was a PhD student of Charles Erechman, but she has studied also with Elie Cartan. And we talk about Lieberman foliation, which are given by these structures. So there is a close link. It's our main interest in our seminar is to how to study dissipation and what are the geometric structure of dissipation. So what are the geometric structure which are transverse to this symplectic foliation and to the level set of entropy. A last remark also, because the first who has introduced contract structures in thermodynamics was Constantin Kara-Theodori, in fact. Yes. In other workshop and conference, we have invited Gromov, who has introduced Carnot-Kara-Theodori space. I always ask him on Pierre Pensu, but why did he give you this name of Carnot-Kara-Theodori space? So they were influenced by the work of Constantin Kara-Theodori, which is more related to the contact structures of the thermodynamic, not the symplectic one. And also, there is always a mistake to use the free energy, because the free energy is not the good potential function, because you are not in the good coordinate system, because you have to use the inverse of temperature. And this mistake come back to François Massieu. So François Massieu was the first to introduce potential function in thermodynamics. we call the Massieu characteristic function, which is a Legendre transform of the entropy. And he has a reviewer, which was Professor Bertrand at École Polytechnique, who say him, "Oh, it's very good, Massieu, but I would prefer that you parameterize by the temperature and not the inverse of temperature." So we have to wait until Planck to understand that the good coordinate is the inverse of temperature.
Yes.
And I have discovered recently that you have exchange on letters between Gibbs and Massieu, and Gibbs was inspired by Massieu to introduce a potential function in thermodynamics. On the last, also, Charles-Michel Marr say me that you have in Gibbs the idea to extend thermodynamics also with moment map. So he extends for rotation, and he has the idea. So it's not developed mathematically, but in one paper of Gibbs, you have the idea of Souriau that you can extend not only for energy, but for angular momentum with hyper parameters. But the fantastic idea of Souriau is to observe that this collection of hyperparameters could be put in one parameter, which is an element of the Lie algebra. So it's a notion of geometric temperature of Souriau. And it was a tour de force in French to have discovered this fact. But yes, and I invite you to look at the problem is that he has only written in French, but the treatment of the co-cycle, because in the model of Souriau you have the co-cycle. So you could extend when you have a non-null cohomology, when the coadjoint operator is not equivariant.
Yes.
And so sometimes it's called the affine model. Many mathematicians say, okay, Souriau has work on the affine extension, but they don't consider it, or they use central extension method to make disappear this co-cycle.
Yes.
But as I said before, for Souriau, it's very important to preserve this co-cycle because he has a very important meaning in physics. For Galileo group, it's related to the mass, so it's very important to maintain. Because this is a difference between the classical mechanics where you have this co-cycle related to the mass, and for the relativity where for the Poincaré group, you have no co-cycle. So you have a null cohomology of the Lie algebra, and the idea also comes from Koszul on the work of Koszul on cohomology of Lie algebra, which is...
Excuse me, I'm confused, but the co-cycle you're talking about is a co-cycle in the sense of Chevalley cohomology.
So the meaning of co-cycle here, it's when you consider the coadjoint, the action of the group on the dual of the Lie algebra.
Yes.
It's not equivariant, so it's not equal to the coadjoint operator. But you have an additional term that is called the Souriau co-cycle.
Yes, but I was just wondering, since we know that there is Lie algebra cohomology in any case, Chevalley cohomology, which is always trivial in the case of simple algebras. I was just wondering whether this is true also for the co-cycles you are talking about, Souriau co-cycle, because the examples you quoted are all non-semi-simple Lie algebras.
So I think for your case, you have not this co-cycle which are to take into account. But just to say that Souriau has addressed a general case on But it's difficult to read in the book of Souriau because he uses his own notation. So is why we have translated in English the book of Jean-Louis Cauzoul, Introduction to Symplectic Geometry, where you have it deals with Souriau co-cycle, but with modern notation. So it is edited by Springer, Introduction to Symplectic Geometry by Jean-Louis Cauzoul. So in the chapter 4 and 5, you have a complete treatment of the case of non-uniform homology with Souriau co-cycle.
Okay, we will look at
what I would like also to say is that the characteristic that the entropy is a Casimir function, I see it's more profound discovery because it gives a geometric definition of entropy. Compared to Shannon, in Shannon you have used an axiomatic definition of entropy. Look for some function that have some properties, but in Souriau you have used to extend the Laplace transform on symplectic manifold, and then you take the Legendre transform on the function you find is a Casimir function. So it could be also a definition. The entropy is the Casimir function associated to the symplectic foliation generated by the coadjoint orbit. So it's a new paradigm that we could define the entropy by this characteristic, or not by the axiomatization of Shannon.
Yes, it is an alternative. You suggest. Interesting, but you see that in the way it comes out from our calculations, it is Shannon also is expressed only in terms of Casimirs of the algebra.
Yes, okay. No, I was very interested by all your presentation. So could you share the slide? Because I would like to share the slide with the member of the seminar with the video, if it is possible.
Yeah, I have made a video of my talk, but I can send you the slides if you give me.
Yes, if you could share also the slide, because sometimes it's faster to read the slides than
Yes, sure.
Okay.
Just let me have your address and
yes, so send me back the slide, and I will send an email to everybody with the slide on the video.
Yes.
Also for people we were not able to attend, it will be fine to have your slide.
Well, should I send them to Frederic? Therefore?
Yes. Only to me for the time being, and I will share to everybody. So thank you very much. So if you are available, so we have another seminar this afternoon with Professor Karl Hermann Nieb with about his last paper, a classification of coadjoint orbit carrying Gibbs ensemble. So he will try to explain more deeply the concept of Souriau about Gibbs ensemble on the notion of this temperature as an element of the Lie algebra, and that you have also introduced in your slide.
Thank you very much.
Frederic, can you specify the hour of Professor Nieb talk? And could you also include me?
Okay. I will include you.
Thank you very much in the advertisement. Thank you.
Okay. Thank you. Okay.
Thank you to everyone.
Thank you very much.
Thank you for invitation.
Thank you very much.
Really nice.
Thank you very much.